If you like technical proofs which contains many notations, you may extend this statement for are many zeros for a given element, and by the zeros, recall that their valuations at P1 and P2 are positive integers. So in the beginning of the proof, let me abbreviate the notations. We will use the corresponding valuation VPI. We will denote it, the corresponding valuation map VPI as VI, and valuation of X at given place at EI, and for the degree of, so that means the extension degrees of the residue class fields, we will use notation the F1 and F2. And here our claim is to show that E1 plus F2 and E2 times E1 times F1 plus E2 times F2 is bounded above this quantity. So here we want to find these many functions which are linearly independent over K of X. So our first choice is to be able to construct such functions for each I by weak approximation theorem. We are able to find prime elements for P1 and P2, which has neither poles and zeros at the different place. That means these prime elements T1 and T2 for P1 and P2 respectively satisfies these equalities. Their valuations satisfy these equalities. And correspondingly in the given residue class fields, since we consider the extension degrees as F1 and F2, we know that there are F1 and F2 linearly independent elements in this residue class fields. So let me consider them and denote them as Ij. Okay. Now in the construction for each valuation, so these S1, S2, and S1, F1 are functions in the valuation rings. And for each function, we will fix 0 from the second row, and by step 3 in the proof of weak approximation theorem, we are able to find Z11 such that for given these two functions, one is 0 function and the other one is S11, we are able to find a function, let me denote it by Z11, such that it in some sense approaches to given S11 with respect to place V1, and it has 0 at P2 and its multiplicity bounded below E2 minus 1. Here recall that E2 is the integer P2 of X. And similarly following by each function, and by applying the same technique, by fixing the first function as 0 and choosing the second function from OP2, in general, we are able to find Zij in F. Or let me write it in this way. For the first one, Z1j, such that B1, Z1j, S1j is positive. B2, Z1j is bigger than E2 minus 1. From the functions that we consider here, and similarly for the functions we fixed from here, we are able to find functions Z2j. They have 0z P1, its multiplicity bounded below the V1 of x minus 1, and the difference between Z and Sij has positive valuation at P2. So now our claim is that by using these prime elements T1 and T2 and the functions we consider here, these Sij's and the Zij's, actually these Zij's, depending on Sij's, our claim is to show these elements are linearly independent over K of x. Linearly independent over K of x. So let me write these functions explicitly, what we want to see for a equal to 1. And if you consider a as 0, first the functions we consider Zij and their multiplications by the powers of the Ti's. This is T1 to the A. Zij can be written explicitly. And we may also extend it. And here also let me observe that the number of these functions, so in each block we have F1 functions, and in total we have E1 blocks coming from E when I is equal to 1. So in total we have E1 times F1 functions, and similar for I equals 2, we can see that here we have E2 times E2 functions. So if we are able to see that such functions are linearly independent, we are able to see that this quantity is bounded above the extension degree. And in order to see that this type of functions are linearly independent, like in the proof of proposition 1.1.15, we suppose not. So let me suppose there exists a non-trivial linear combination whose coefficients are from the rational function field k of x. And like in the proof of the proposition 1.1.15, without loss of generality, we may suppose that these coefficients are polynomials and not all divisible by x. or separating when I equal to 1 and I equal to 2. For each summons, we may consider that these coefficients, not all coefficients, divisible by x. So we may separate the two cases. So there exists a k. So either for the first summand, for the second summand, there exists a j depending on which summand we consider, such that there's a kind of maximal term maximal indices C, such that all terms before this index, all coefficients before this index are divisible by x, and for j in 1 to fk, and the other terms, there can be some term which is not divisible by x. So now fixing pk, or the degree pk, or the fk, our claim is to get contradiction such that these elements in the corresponding residue class field are linearly independent over k. So this is our aim, to get a contradiction from this equation.